Okay. Morning. Okay. Let's quickly recapitulate what we have seen so far. Last time we have seen counters. So we have seen that we all started with gates. From gates we have formed latches. From latches we have formed flip-flops, just because we wanted that edge behavior, okay, edge dependent behavior. With flip-flop, we found that there are several types of flip-flop. We wanted to set a bit, we wanted to reset a bit, we wanted to toggle the bit. Depending on that, there was one flip-flop which was able to capture all four of them, all three of them. That was JK. Apart from that, we have also seen that there are, we may not know what are the previous states. For that purpose, we are having the preset and clear buttons there. So, if it is given bubble there, we need to keep 0, isn't it? So that's how the active low inputs are defined. Active low in the sense it will be clear when you give 0. It will be set when you give 0. So the activity happens when you give low as the input. That's why it's called as active low. If you high as the input, then whatever the behavior is called as active high, and so on. Then we have seen so we have seen the register, right? When we cascade those flip-flops, we have seen the register, and we saw that a flip-flop is also a 1-bit register, and the output of a flip-flop will be acting as a frequency divider. Right? If a clock has been given to a flip-flop, the output of a flip-flop is like a divide by 2, isn't it? So it's like a frequency divider. So if there are n such cascaded flip-flops are available, it will act as a divide by 2 to the power n type of frequency divider. We have seen that. We saw the counters. Okay? We saw type of counters. So can you tell me what type of counter we have seen? We have seen a counter where the output of one flip-flop was given as the clock was actually acting as a clock to the next. So there was kind of ripple or jumping of bits which was happening. We have seen that, right? So such kind of counters are called asynchronous, where the clocks of all the flip-flops are not, when the clocks, so all the flip-flops are not triggered simultaneously. They are triggered one after the other. That's how the rippling happens. That's why they are also called as a ripple counters. There is a jumping of bits. Now we have seen an example of 2-bit, or how many bit counter? 3-bit or 2-bit? 2-bit we have seen that. So I have also given you an homework to go for a 3-bit one. Go for up counter, down counter. Have you done that? Tried at least? Give it a try sometime. So we have seen a negative edge triggered so far. We can also go for positive edge. Just we have to make sure that the positive transition is getting captured. That's it. Okay. But the connections will be completely opposite to what we have seen. Like if you are giving the output to the clock, and if you are giving the complement of that to the clock, okay, the behavior if you are using the positive edge will be completely opposite as we are getting for the negative edge. Okay. So now we have seen that. Now what happens? Now let me 28. Right? So how was the behavior? We have seen the 2-bit counter. No? 2-bit counter was having the state. Now I am drawing the state diagram for that. They were having 0 state. As soon as the next clock edge comes, okay, it was jumping to the next state, that is 0 1. As soon as the next clock comes, that means when the clock is 1, or no, I should not say 1 here, because that is not a clock. That is the clock to the previous flip-flop, you can say. Clock to a particular flip-flop, you can say. So I won't write anything here. 1 0 and 1 1 there. So this is how the transition happens. But what if I give another clock after 1 1? It will reset back to 0 0. That you should confirm. Okay, you should confirm that when it is at 1 1, as soon as you give one more clock, okay, at the next edge of the positive edge or negative edge, it will reset back to 0 0. So that's if such kind of circuit happens, that is called as up counter or a down counter. So it's a counter. Now what is happening here is, it is jumping from this 0 1 2 3 and back to 0. Now we may sometimes want to we may not want this to happen for the complete cycle. We may want to reset after 2, we may want to reset after 1, and so on. Say for example you have 3-bit flip flop, and if you want to, say for example you want now what is the mod of this, you tell me? This is mod 4, right? We may need a mod 6 counter. So for that, what is required? I mean, for 6, what is mod? I said mod is number of states, right, including 0. So that means it will go from 0. How many? First of all, how many flip flops will be required? You tell me. 3, isn't it? I mean, that log 2 to the 6 will be seal of that, isn't it? So that will be 3, and it should go from 0 0 0 to it should go to 5, right? So 1 0 1, and after that it should jump to 0. So further states are like forbidden. We don't care. We don't care. I mean, we don't care. You say it should directly skip back to 0 0. So what I'm doing is I'm actually forcing this counter to go back to the reset state. Okay. I mean, this is a serial counter. It is counting, but in the between I don't want to complete all the states and coming back to the reset state. How is it possible? So just think of it like, say for example I want to go for a mod 6 counter, and I have given you a hint saying that there are 2 more pins which are available there with the counters or the registers or the flip flops. There is a preset and clear, isn't it? So let's consider this. Let's consider this clock cycle. If I'm taking a clock's cycles, assume that we are going for negative age kind of flip flop, and let's go for mod mod 2, you can say. No, mod 2 is not required because 2 will be okay. We can go for mod 2, or let's go for mod 6, no problem. Then what is the output of first flip flop, you tell me? Now this is a first negative age, right? So here, there, and so on. The output will be toggling here using, if I am assuming T flip flop, this is the output for first flip flop, isn't it? Can draw a complete timing diagram for all the cycles for 3-bit asynchronous up counter. So how is the circuit? Tell me, how is the circuit? I mean, you will require at least 3 flip flops. Okay, so I said that it's a negative edge. So how would be the connection? Yeah, so the input will be from the normal end, right? Normal output end, Q. So these are the 3 flip flops, I am assuming. Now we should know our aim. Our aim is not to complete the complete count. We should be able to reset the count in between. So let's see how that can be done. the negative edge flip-flop. So I'll be directly connecting this output of this to the input of not the input, the clock of the next. So again a ripple or a asynchronous counter. And what about the inputs? You tell me. Inputs. Yeah. Hi. So we need to connect all of these inputs to 1, isn't it? Just because it's a toggle flip-flop. We are assuming that as a toggle flip-flop. If not, we have to make sure that the flip-flop operates in a toggle mode, isn't it? And 1 here. T. You tell me now. See, you should not get confused while drawing this. MSBs and LSBs. Always remember, the LSB is one which toggles quite frequently, and MSB is one which toggles less frequently, lowest frequency. So which is the one which will be toggling at the highest frequency? This one, right? So that will always be an LSB. So let me write that also. So LSB is something. LSB is the output of flip-flop which toggles at the highest speed, right? Or it toggles quite frequently. And reverse is the LSB, right? Now, okay, so this becomes 0, that is clear. Q, now we don't need that. Let me write that, but we don't need that. Q1 bar, Q2 and Q2 bar. Alright, so where are we taking the outputs from? Here, right? I mean, yeah, no? यहाँ से outputs are nothing but this Q0 Q1 and Q2. In between they are not joined, okay? So this becomes Q0, Q1 and Q2 there. Alright, so draw now this is for Q0, of course. Draw it for Q1 and Q2, quick. This timing diagram is very important. It will give many insights when practicality is concerned. Alright, so I should draw some more. How many clocks you feel that I should draw? You tell me. Huh? 12, huh? So 3-bit. Mod 6. Huh? 6 2s are 12. Oh, no, clocks. That means one cycle, right? So I think, no, this can maximum go till 8. So after 8 it will be out. So 8 is sufficient, right? So this is 1. extra I've just drawn for illustration purpose. Now you should know the purpose, right? What is our purpose? What is our purpose? You tell me. Yeah, we should forcefully reset the counter after. Yes, after 5. Okay, you should include the count of 0 also. Now first, let's draw all the waveforms. Let's see how it looks like, and then we may think of the modification. Can you tell me the output frequency? What would be the output frequency? It is mod 6 now. So if it is completing all the counts, then it is to divide by 2 to the power m. Here it is not completing, it's always divide by m, right? Divide by m. So how many states are there? 6. It will be divided by 6. It's a mod 6, so output will be divided by 6. We'll come to know. Let me write this. So this is Q0, Q1, Q2 there. Now tell me the outputs here. Tell me the outputs completely. So it is 001, 001 here, and earlier of course it was 000, and this, let me write it 0, 1, 0, and so on. Well, see here. So what is the count here? You tell me. Now let me write that here. So it's Q2, Q1, Q0, and they are following the usual pattern 000, 001, 3, 4, 5, 6. And we don't want to go it beyond this, right? I mean, we don't want this condition to happen. This is a mod. What I'm saying is this is mod 6 counter. That means we want this to happen only till 0 to 5. Okay, we don't want this 6 to happen, isn't it? That means, let me write that. So it should reset. After this, it should reach. Let me rub that. Okay, let me first. This is the one that we don't want, right? Now, till what point it is okay? The output is okay. You tell me. Till this point, see here, 0, 1, 0. This is what 2, 3, 4, right? This is 5. This is 6. Okay. We don't want the output. Here we want all zeros, isn't it? We don't want this count to happen. That means the moment this Q1 and Q2 becomes 1, 1, isn't it? The moment this Q2 and Q1 becomes 1, 1, it should reset back to 0, 0. So how that can be done? Yes. So the simple, simple thing would be you take an AND gate. And connect it to what? Clear, right? But this, as I said, these are active low, so we'll require an NAND gate, right? And then we are going to connect that. So this will act as a, you tell me, mod. So it will be, the output frequency will be divided by 6. So so this will be Q2, will be connected here, and Q1, right? So Q1 and Q2, right? Okay, so that is need not be, I mean, we need not take that. I mean, both possibilities are there. We may consider this Q0 we may also consider both of them. See, what is the minimal condition you tell me? Minimal condition is if Q2 and Q1 are both 1, 1, then it should reset. Okay, this doesn't matter, isn't it? If both are 1, 1, okay, this doesn't matter. I mean that the minimal condition which is required is Q2 and Q1 should be. Equally, if you take into consideration this Q0 bar, that is also valid, no problem. Okay, that is also valid. If you take Q1 and put a NOT gate there and take a 3 input NAND gate, that is also valid. So I'm just looking for the minimal condition. Just because for 3 input I will require, if I am having only 2 input gates, and if I go for 3 input I will require 2 NAND gates and so on. So what happens is, like, you should complete the 5th count, isn't it? You should complete the 5th count. That means this one you should be able to complete this, and as soon as it goes to the 6th one, it should reset. That means we expect a count to last for at least 1 clock cycle, isn't it? That means you need to rub this. I will rub this. Now, this we don't want to happen, right? That means the moment it goes to 1, 1, I don't want these things to happen. So what happens now? Now these were the things which were happening earlier, right? Now what is happening? As soon as the moment it this Q2 and Q1 reaches 1, 1, we will reset back to 0, 0. So I should draw something like this. So the moment, and now this is very small. Now how small it would be? You tell me. This would depend on the delay of the gate. Okay, how fast it reset this, isn't it? So it will be going to the 0, isn't it? It will be going to 0. So from here itself it will go to 0 and so on. And from the next clock cycle, you tell me what happens? It will again start back from the 0, 0. So that is how it happens. It continues. Now this is 0, 0, 0. Draw that. Is that clear? Any doubt till this? Which one? Q1. Okay, you didn't get this. Yeah, okay. So this is just a indication saying that. See here. Now you forget about this connection. You forget about this green connection. Okay. You forget about this green connection. Only consider this circuit in the blue. What happens? It usually counts this output of Q1, Q0. The first toggle flip flop will be, it will keep toggling just because it is set to 1. For each negative edge of the clock, it is going to toggle. That is what is happening. For each negative edge, it is toggling. Q0, output of first flip flop, it is toggling. Let's continue that. That's what the diagram I have drawn earlier. What about the Q1? The output of this? It depends on what is the clock to that is the previous wala output. What is the previous wala output? This one, Q0. Okay. Depending on the negative edge of previous wala output, it will toggle. So it depends. This will toggle depending on the negative edge of the previous wala output. Okay, it will toggle. Now, as soon as now I am making the change. Now it will go on continuing unless and otherwise I make some changes. Now what I want here is to go for a mod 6 counter. Mod 6 counter means it should include the 0th count till 5th. After that it should reset back to 0, 0. We don't want the other states to happen. We don't care that. Okay, we directly want to reset back to this 0, 0, 0. Just say for example, I need to count till 60, isn't it? The seconds for a minute, I need to count till 60. But how many flip flops will be required for 60? You tell me. For 60, you tell me. 6. But how till what it can count? You tell me the maximum count. 63. Okay, 0 to 60 means total 64 counts it can count. But for clock we require only till 60. So how can we make that till 60? This is how we can make it. Okay. Here I have given the example of 6. After 6 you want to reset. That means this will last for 1 clock cycle. This will last for 1 clock cycle and so on. as soon as this fifth count is completed, one cycle is completed, as soon as it tries to go for 110, I should be able to reset that. So the moment it goes to 110, this gate will get triggered. 1 means the output will be. Oh, I didn't draw the connections here. So this one. So this is. You tell me what is that? So clear, right? Clear bar. Why the bar? Yes, it is active. Now this is again an interview question, right? I am saying that this active low है तो कुछ नहीं, पर ऐसे these jargons are actually asked in the interviews. It is bar. Everything is bar. Alright, so the moment it goes, it attempts to go to 1, okay, it tries to go to 1, this is already at 1, it tries to go into 0, now as soon as it goes to 1, it resets and so on. So this is an indication of like a small trigger or small flicker which is happening during the reset. How much would be this duration, you tell me? This duration should be equal to the propagation delay of this gate. Is that clear? Go for go for a BCD counter. Draw a circuit for a BCD counter. Means, what is BCD, you tell me? 0 to 9, draw a circuit for BCD counter. Quick. Draw a negative edge using toggle flip-flop BCD up counter. Right. So what is the step? You tell me the steps. The very first step is to determine what is the mod. Okay, the mod of the counter. So right, step 1. Determine the mod of the counter or the total number of states. For BCD, how many steps are required? You tell me. Huh? 10. So it becomes mod 10 count. Step 2. Yeah. So step 2 is you need to determine the total number of flip-flops required for that. How many? Tell me. Go. Right. Go for it. Now I have asked you. No, you should write the complete problem, right? I have asked you to design a BCD. Sorry, the negative edge triggered BCD asynchronous up count. Okay, that is the full name. Okay, you should write. Negative edge BCD asynchronous up counter using T flip flop. will help you in avoiding mistakes. There are some different ways to reset also. See, for example, what I said, I am just checking when this pattern appears, but I may also think in the direction that okay, this thing is happening only if this is both 0 0, okay, and the previous states are 0 0 and this is 1, then only this should happen. I mean, there are different logics which we can using which we can reset this. Okay, this is not the only logic. Okay, come up with a different logic using which you can get the same thing. Yeah, you should get the same operation. Yeah, anyone who is able to draw complete circuit? Not drawing the solution. Okay, this is different thing. I'm expecting the answer from you. All right, anyone who is able to do that? count, right? I mean, this is a mod 10 counter, you need to count till 9. When do you want to switch it? Just after the next count, right? So, at 10, right? 1, 0, 1, 2. Okay, incomplete labeling 0 mark. Again मैं बोल रहा हूँ binary mark दूंगा मैं. ठीक है, एक भी लेबल मिसिंग हुआ कि मुझे क्या पता वहाँ पे 0 लगाया हुआ है. I'll give 0 marks. Again I'm telling you. जैसे भी पिछले पहले सेशन का एवरेज वैसे कम है. So, homework for you is to give a try with positivity. Give a try with positivity and give a try for odd mod. Mod 2, mod 3, mod 4.
Q3 कोई बात नहीं चलेगा. So means यहाँ से गिनना चालू कर दूँगा.
Okay, he has taken 4 of them, right? So you need not take all 4 of them. Again, I am saying that this is valid, of course valid. Say if you are having only 2 input NAND gate, then the condition with Q3 and Q1 would work. So this is another implementation, another way of implementation. Is it okay? Thanks. So just because that should be valid only if this Q1 and Q3 is unique. I mean, that should not come earlier. देखो Q1 और Q3 1-1 सिर्फ तभी होता है कि देखो Q1 and Q3 becomes 1-1 only during 10, right? Before that doesn't happen. That means that is the minimum condition that we can have, isn't it? So yeah, so good. See, what I'm saying is this. Yeah, okay, it's till mod 6, right? So till 5. After this we want, what happened? 4, 5, 6, 7, right? Okay, till mod 9. Okay, 7, 8. And here we want to reset that, right? So what he has done is, he has taken all 4 of them and all 4 of them and formed a NAND gate, right? It's it's like a safe side. सब के सब मैंने ले लिया. I don't want to worry about anything. So, but what is, you should also think of as a minimal implementation as a designer. Okay, so there you need to put small your mind there, and so see, so this 1-1 happens, okay, only during this condition when the count is 10. Otherwise, doesn't happen. So even if you take a simple NAND gate, 2 input NAND gate, and drag the inputs as Q3 and Q1, that will do the job. So this is equivalently valid. So a lot of lag here. So if I do this and if I take a input as Q3 and Q1, that is equally valid. Okay, I mean this will of course reset. बहुत गंदा कर रहा हूँ ना. It's okay. I mean you should be able to understand what I'm doing. Okay, I'm saying that 2 input NAND gate is sufficient. Okay, fine. Now homework for you is to think of a circuit. क्यों मतलब 0 पे जाने की जरूरत है क्या? You should be able to reset it to any count. So after 6, think of a circuit which can reset to 2 or 3 or so on. That means it should be somewhere in the middle. Like it should count from 2, 3, 4, 5, 6 and back to 2. It should count from 3, 4, 5, 6 and back to 3 and so on. So that is also a counter, isn't it? It will be counting in between, a band restricted counter, you can say. Alright, so that's a homework for you. Homework for you again is to come up with the positive age triggered all mod counters. That will help you in practice. Okay, practicing the things. Alright, so this counters which we have seen so far are called as asynchronous or ripple counter, just because those bits are getting jumped from one flip flop to the other, and also the clocks are the outputs of the previous one. This is a serious problem with such kind of flip flops, okay, or such kind of counters. The problem is the delay. I mean, a flip flop cannot trigger as long before the previous flip flop is actually it has been clocked properly or not. Okay, so I mean a flip flop will work only if the previous wala output is available. Otherwise, it may not. Okay, it won't, right? Because the clock of flip flop is nothing but the output of the previous wala flip flop. So unless and otherwise the output of the previous wala is available, the current flip flop can't trigger, isn't it? It has to wait until the previous flip flop counts or the previous flip flop output is available. Okay, that is how the rippling happens. So that may introduce a delay. Okay, that may introduce a delay. Like nothing is ideal. A flip flop may have some delay involved. So let's consider this example. I'm just giving an example. Assume that this is a clock, and the output of the first flip flop I'm drawing. So assume that it is having now this. Let me write this. This is negative age there, and so on. Assume that one clock cycle here, this one, कहाँ से कहाँ तक रहेगा? Negative age से negative age, no? Yeah. So assume that this is some value. Okay, let it be 0.2 microsecond, millisecond, whatever it is. So let it be 0.2 microseconds and so on. And let's assume a delay of one flip flop as 0.05 microseconds and so on. So what would the output, you tell me? Now see, let's consider the same case. Okay, same case of 3 flip flops or 4 flip flops. Let's consider two flip flops time being, okay, or 3 flip flops at a time. Let's see that what happens. The output, now it should trigger, the first flip flop should trigger somewhere here, ideally, but that may not happen just because it is having a delay of 0.05 microseconds. So it will trigger from where? Here, 0.5 after this negative age, isn't it? It will last till here, no? But there will be a 0.05 microsecond of delay for one flip flop, right? So the output of this will be delayed by 0.05, you can say as a microsecond. And so on, isn't it? So let me draw this. So this is where we expect the output, but we are getting it here. what I'm saying is this one is how much it is? 0.05 micro. Now this is called as a propagation delay TPD of one flip-flop, okay, of one flip-flop. Assuming that all the flip-flops are identical, the another output, okay, the other output of the other flip-flop will be delayed by this, right? So, you know, the output of this. So let me draw that. So output of that, negative edge कहाँ पे? यहाँ पे है ना? यहाँ पे expected था पर यहाँ पे आएगा. .05 delay with respect to the previous wala clock, isn't it? So what is the overall the delay which is happening? We expect the output to be at the next clock cycle, right? But output we are getting at the at 1.1 microsecond after that, isn't it? So let me draw that. So here this, how much this is? 0.1 and so on. Can you quickly draw this for 4 flip-flops and see what is the state? What are the states which are coming? Okay, you'll get confused somewhere in the between. You should consider the last state it was holding. Okay, there will be overlapping of the states. There you should consider only the state which is just before the transition. So draw all the states. And of course the fourth one, and tell me the states please, quick. Oh, this should not be like this. Okay? This should not be like this. This should be at negative edge. Delay. So let me draw the edges first. This is the edge, or not this one, there, negative edge, this is not valid, this, and so on, right? Yeah, so what is the delay here, you tell me, of the output here? How much is the delay? This is where we expect the output, right? After 4 clock cycles there will be output here, and we are getting actually the output here. So this again, this point, tell me 1.5 microseconds and so on. Okay, yeah. So this is going to happen, right? And what happens? Can you draw the states? Time is, draw the states. Tell me the states. How will you draw the states? Write the states, you tell me. This clock cycle, okay, for 1 clock cycle and so on. So here it is 0, 0, 0, and of course it will be 0. And here, now till 1, here, during this period, what is the output? This is the 1, okay, from 0 it is happening 1 here, right? So although it is 0, it is, I am considering 1 here. 0, okay, this is 1. Then here it is 1, 0 0 0. Tell me what is the output here. 0 here, 1 here, 0 1. What is the output here? You'll find that it won't go with the normal normal count. Okay, there will be skipping of counts which would happen. Okay, in between states will go off just because there is a delay, right? There's a delay being there. We will always take into account the count in between the two clock cycles, right? I mean, during only one clock cycle we'll consider that count, right? As because there is a delay, there is a delay of exactly by 4, right? I mean, this clock cycle, there's a period of clock cycle is 0.2 microsecond. The delay is exactly by 4, right? So after 4, you will find that there is a skipping of states which is happening. States will get skipped. In between states are getting गायब हो जाएंगे. Also, it is skipping some step and some ambiguous pattern will appear. Now this is all due to there is a delay involved there. So here, what do you expect? What do you expect? What should be the ideal condition? Oh, see, delay we can't avoid. So what should be restricted? You tell me. See, there are 4 flip-flops. Now let me do that again. See, what I am saying is they have. I will draw it quickly. There are n such flip-flops you consider. Okay, you are giving the output of this to the clock of this, and so on. You are taking the output from here. Toggle T U0, T U0, and so on. Q1, sorry, Q2, and so on. So this, this. You tell me, to avoid this skipping of states, what should be the condition? Yeah, exactly. So how much is the total amount of propagation delay? The total number of flip-flops, right? So n times, let's say that there are n number of flip-flops. This is n times the propagation delay, PD, right? There was 0.05 microsecond from one flip-flop, 0.01 microsecond for 2 flip-flops, 0.15 microsecond for 3 flip-flops, 0.2 for 4 flip-flops, and so on. That means you should get the output of the count, between the one clock cycle, right? That means the clock cycle period, okay, T, C, should always be, you tell me, greater than NPD, TPD, okay? TPD is the propagation delay of one flip-flop. So n times the propagation of delay of the flip-flop, that should be always less than this clock period, isn't it? That means what? The frequency, if I talk in terms of frequency, this should always be less than the frequency of propagation, or you can tell this as this 1 upon NTPD. This is equals to FTPD. So the propagation delay frequency should always be higher than this clock frequency. Okay, you got the point? Fine. Okay, so I think the time is up. So let's stop here. Any problem till this? Clear? All right. Let's stop.